with the class. So, welcome back to the class on tribology to one and all. So, in the last class, can you remember there was a long gap in between the classes? What we had done, can you remember? We had started with the second part of the module 4, which deals with basically plane sliding contact bearing. So we discussed about the key concepts of the sliding contact bearings, its characteristics, advantages, and we studied about how the pressure development come across in a given plane slider bearing mechanism. So here we studied that the plates could be parallel to each other or it could be inclined, right? So we studied the conditions, how the pressure development takes place in case of a convergent film as well as in an uniform layer in which the oil film will be moving across the two parallel surface. So either in the two parallel surface or in the incline, the bottom surface will be held stationary and the top surface will be moving with a constant velocity. So this we studied the mechanism of the pressure development in the previous class with respect to two conditions. So now the same concepts we are applying to derive an equation for pressure distribution, load bearing capacity and the coefficient of friction in case of plane slider bearing. So plane slider bearing, as discussed earlier, it comes into the category of hydrodynamic and not hydrostatic, because here it will not be in a static condition. It will be relatively having a movement across the oil film, across the contact area. So this thing you should be keeping in mind. So with respect to the concepts what we studied in the previous class, so now we need to go ahead with deriving the equation. So the same concept here, we have the two surface. This is the top surface and this is the inclined one, right? So this will be moving with a constant velocity u, so it is being fixed, and as a result the oil film flow will be like a convergent type, so we call that as a converged film. So this will be relatively to the condition in this way what we have discussed in the previous class. So the velocity across the bottom with which the oil film will be moving will be stationary, and here it will be almost same to the uniform velocity with which it is moving across the top surface. And in between there will be an reduction in the velocity. Towards the bottom it will be the least, and towards the top surface you will be having comparatively a better velocity when you compare with respect to the bottom surface. So this concept remains the same, wherein you will be having a difference in the oil film thickness. So we categorize that into H1 and H2, right? So if you take an reference plane here parallel to the bottom surface, so then you will come to know what is the inclination of the angle you are getting with respect to the parallel surface. So this we have discussed already. The same concept we will start up with pressure distribution concept for idealized plane slider bearing. So as the figure which shows you the two surfaces, basically it is not parallel. It is non-parallel because you have one surface which is in horizontal direction and other one is in incline, and hence it is a non-parallel surface what we are considering. So this will be the length of the top surface, wherein the oil which moves across the parallel surface here will be having different oil film thickness. So this is maximum H1 and this is the H2 what we are considering. So these factors you have to keep in mind, right? And I think this we had discussed about the concepts, but still let me go through. So one of the surface here you can consider to be as stationary. So one surface we will be considering to be as a stationary. So by the diagram you can see the velocity is given for the top surface. That shows that the top surface is in movement with a constant velocity, and this bottom surface is being held stationary. So one surface we are keeping it stationary, wherein the other moves with a constant speed. We usually represent that by capital U. And further, the direction of the motion and the inclination is given in such a way that convergent film is formed. So this is the converged film we are forming because the thickness is varying due to the inclination. And due to this inclination, the film thickness what we get is in the form of a converged film. It is converging at a particular point here, right? And hence we form a convergent film. So the direction and the structure and the motion of the velocity will yield us in providing an convergent film. And what we were calling as the stationary plane, right? The stationary plane could be fixed permanently, or it could be pivoted, or it could be constrained in such a way that it is held in stationary, means it is bounded to some conditions and constraints which makes the bottom surface to be fixed, right? So it depends upon you how you do the pivoting or how you fix it so that it is held stationary, right? So this is the next thing what you have to understand. So when we assume that the bottom plate is fixed, so it is stationary, so then you will be getting the relative motion with respect to the surface wherein the top surface is moving. So the velocity, the relative velocity with which the oil will be moving here will vary. So it will be higher towards the top surface and least towards the bottom surface. So the layer of the fluid, the film of the oil which is touching at the bottom will be having a comparatively negligible relative motion. So to get the relative motion, it is necessary to keep one of the surface to be held stationary. That is the reason we are fixing the bottom layer to be as pivoted. So these things you have to understand clearly, right? So then you will be getting a relative motion as required with respect to the moving plane, right? And in this condition, now we have to determine what is the hydrodynamic pressure which is coming across when the plane slider bearing is moving. What is the load carrying capacity of the plane slider bearing? What is the frictional force and coefficient of the fluid friction which come across when the plane slider has a comparative relative motion? So these things need to be derived. Okay, so for this, the concept is, so we take that there is no variation of pressure across the z direction. So this is the direction z. So the person who have derived this claims that there is no pressure distribution across the z direction. So pressure distribution across the z direction is assumed to be negligible or zero. So with this prerequisite concepts and assumptions, they have taken the Reynolds equation to start up with the plane slider bearing derivation. So Reynolds equation for we have derived already in the previous classes, right? So the same equation is being used and it has been differentiated, and further it is integrated to get the required pressure distribution formation for the plane slider bearing. So with this aspect, if you remember, the Reynolds equation was being given with respect to variation of the pressure, right? So here dP by dx will be equal to 6 mu u suffix b into h minus h suffix m divided by h cube. So this is a lengthier derivation. Sometimes they ask and sometimes you get problem. So kindly do understand and you have to write. If you write fully, you will get full marks. So kindly do understand and write. So first you will take the Reynolds equation. So here U term is related to the motion with which the upper surface is moving. So now the parameter which is there in Reynolds equation should be put forward in a way such that it matches our motion velocity with which the upper surface is moving. So we have assumed that the top surface is moving with a velocity of capital U. So we have to try to correlate U suffix B in the form of U. So here what he has assumed is, so U suffix B will be equal to twice the velocity, because it was a very small component of velocity which was considered during derivation of the Reynolds equation. So now that you have to correlate to a constant velocity with which the upper surface is moving. And hence this was equal to twice the velocity which was made equal to capital U. So in future when we use the same Reynolds equation for our plane slider bearing equation, right? So we will be replacing U suffix B by capital U. And the thing related to that is being shown you in the correlation within the bracket. And then you know that H stands for oil film thickness. So here you have two types of H. One is the regular H, another one is the H suffix M. So here it means to say H suffix M is some film thickness. It is not the actual one. Okay. So because here itself we have two variations. One is H1, another one is H2. Right. So this is the actual film thickness, what is there in between the two contact surfaces. But when the bottom surface has been inclined, it is the oil film gets converged automatically, and hence the thickness of the oil film is reduced over here. So similarly, here in the equation, HM is referred to some film thickness. So keep it as it is for time being. And next you have to put forward for what condition of pressure you're trying to correlate the equation. So first we are assuming the boundary condition as P is equal to 0. So we are taking dP by dx is equal to 0. And the other assumptions which was followed was H here will be standing for H minus alpha x. So you know what is H1. So the actual H will be equal to H minus alpha times of X, this distance. So this is H1, this is H2, this is H2. Okay, so this distance they have taken it as X, and this is alpha, the inclination with which the bottom surface has been inclined. So they will be taking H is equal to H1 minus alpha X. Okay, so from this they will figure out what is alpha. So alpha will be taken as H1 minus H2 divided by B. Okay, B is the distance, okay, width of the top surface which has been taken. And this is the length of the top surface, and this is the width. So this B term comes into picture. So you will be writing alpha is equal to the difference in the oil film thickness divided by B. So now you know the value for H, you know the value for alpha, what has to be substituted in the equation. So once you know the values for this, in the beginning only they told that the the Reynolds equation has to be differential. You have to take the differential equation of the Reynolds equation, and then it has to be integrated. So before integrating, we have assumed the condition of boundary condition, what we need to take for pressure is equal to 0. So based on that, you will then integrate. So when you integrate this equation, so this will be equal to P 6 mu in place of U suffix B. Now we are taking U. So this all three are constant. So before integration, you will keep the constant parameters outside. So integral of, you will substitute the value for H. So H will be H1 minus alpha X into HM, right, divided by H cube. So H cube is nothing but H1 minus alpha X the whole cube. So after substituting the value of H, right, you will do some simplification. So then you will integrate and keep the value with respect to X you're doing. So you will get dx. So once you integrate, you have to put the constant term. You will put C, it is C1 because it is the first constant term what you are adding. So C1 is the constant. So once you integrate, what is our duty? You need to determine the value of constant. So to determine the value of constant, it is very essential to put the boundary conditions. So the first boundary condition what we'll be assuming is pressure is equal to 0 at X is equal to 0. And in future, when pressure is equal to 0, for the distance of this plate for B, what will be the variation you should come to know. So we have two boundary conditions what we have to apply. So once you have integrated, you will put the value like P is equal to 0. Okay, so here also the X term will be equal to 0. So then you will find out what is the value of C1 you are getting, right? So when you put this condition, you will determine the value of C1. So after getting the value of C1, you have to go and substitute back in the equation 4.2. So when you put this condition, you will get the value of C1 is equal to minus 6 nu divided by alpha H2 into 1 by n plus 1. So this is the value what you will be getting. So after you get, you will go back to the equation. So before going back to the equation, you have to change this value, okay, because you need the attitude or the eccentric ratio, right? So n will be assumed to be equal to the ratio of h1 by h2. We are doing this because you have a convergent film. If it was not a converged film, if you had two surfaces parallel, then we were not taking the ratio of h1 by h2 because the oil film thickness will be same throughout. Here also it is H1, here also it is H1. Since it is converged film, you have to take the condition of N is equal to H1 by H2, which will be claimed to be as attitude, yeah, the eccentric ratio, right? So then after knowing this, the value of C1, which was claimed here to be 1 by n1 plus 1. So in place of n, you can put h1 by h2. So later you can simplify. So then you will get the value of C1 in terms of H1 by H2. So when the denominator here, so N is here, right? 1 upon H1 by H2 plus 1. So you have to take the LCM for the denominator first, simplify it, and then you have to figure out the value of C1 in terms of H1 and H2 only. N will be omitted. And one more thing, in place of HM, which they claim to be as some film thickness, you need to take the value in this form. So HM is directly given to be equal to 2NH2 divided by N plus 1. Because we are converting all the parameters which is there in the Reynolds equation in terms of H1 and H2 only. Because here we cannot show any HM, which is some thickness of the oil film. How you can claim some thickness of the oil film? It has to be in terms of the parameters which is shown in the diagram for the plane slider bearing. And hence the assumption one more for HM is twice the attitude value into the converged oil film thickness divided by the attitude value plus 1. So in place of HM, what you have in the integrated equation, you will be replacing by this terminology. And in place of C1, you will be putting this equation. And later in both the equations, N has to be replaced by H1 upon H2. So once you substitute HM and C1 value to the equation of 4.2, so then the equation gets changed into this form. Okay. So this is the equation what you get after substitution of HM and C1 into the pressure distribution equation. Hope it is clear until now. Any doubts? Hello?
Yes, ma'am. Yes, ma'am.
Hello? Is it clear? Are you people there? You're still sleeping?
Yes, ma'am.
You're sleeping still. You told me yes. Is it?
No understanding, ma'am.
Okay, okay, okay. Thank you. So how will I come to know whether you people are listening or not? So this is the substitution of the value of HM and C1 into the pressure distribution, right? So then what is the claim which is being given as the pressure is directly proportional to the viscosity? That you know. It depends upon the lubricant what you are using. Suppose if we go back to the diagram here, you have a layer of lubricant. It will be having certain viscosity. It depends upon which grade lubricant we are using. So based on the grade of the lubricant we are using, it will be able to give the required pressure, because the pressure distribution plays a very vital role that helps to withstand the load which has been subjected on the plane slider bearing, right? So directly the pressure development will be proportional to the viscosity with which type of oil film you are using. And also what is the sliding speed with which it slides will be inversely proportional to the converged film thickness of the oil. So one thing, the pressure distribution depends directly on the grade of the viscosity you have. And secondly, the sliding speed. When you speak about plane slider, it will not roll. It has to slide. You have seen the sketch also. How does it look? Right? So if we go back to the sketch here, it has to slide. This upper part has to slide over this lower part. So with what speed it slides, it again depends upon the converged oil film, right? Because in this section you will be having an oil distribution. So based on the given oil film thickness and the pressure distribution, it will slide, and the speed with which it is sliding, it depends upon the converged oil film. So what is that converged oil film? That also we have dealt upon, right? This is nothing but H2. So based on this H2, the speed will be relatively having a comparative speed. Why? Because if you go to the section here, you can see this is the area where you have the oil distribution. So this is the area in which you'll be having the top surface and the bottom surface will be inclined in this way, right? So you'll be having a converged film across this end. So across this end only you have the oil distribution. So based on H2, it depends with what speed it has been sliding. So that is what been explained over here, right? So you have to write directly, the pressure directly depends upon the viscosity, and the sliding speed depends inversely proportional to the converged film thickness. Not only H2, it is H2 square. So now we are clear about the pressure distribution parameter, because we have derived an equation for pressure distribution, and you know how the pressure distribution is proportional to viscosity and the sliding speed. Then you have to think about the load carrying capacity. We had derived last time a load carrying capacity equation for hydrostatic bearing. It was little bit simple and not much complicated. But now here also, now we have to think about what is the load carrying capacity, how we do calculate. So in general, the load carrying capacity mainly depends on what parameters, what is the length of the top surface, what is the pressure distribution across the contact area. So it is with respect to what? It is usually dP by dx, and hence we are taking P into dx over here. But you have to integrate for load carrying capacity as well. So you have to think about what is the upper limit, lower limit, and the upper limit for the integration. So you know that in the given sketch, the width of the surface is from this distance to this. So maximum is B, and if you consider this end as 0, it is from 0 to B. So the same part has been taken here, the integration of 0 to P, the amount of pressure distributed here due to the selection of the lubricant into dx. So this will be the equation what we follow to determine the load carrying capacity. So wherein L is an length of the bearing as discussed earlier, length of the bearing here, which will be constant, and hence it is figured out before the integration factor, right? So now what we do is we have the equation for P is equal to L integral of P into dx. So what is P? P we have derived already. What is the pressure distribution term, right? So you have to substitute P value in equation 4.7. So which is your equation 4.7? This is the load carrying capacity. So the value of P has to be substituted in this equation 4.7. So after substitution, you have to integrate, right? So once it is done, you will no need to show each and every integration step, because this itself a very lengthy one. So you will directly tell that this is the load carrying capacity equation. You have substituted the pressure distribution equation over here, integrated from 0 to B, where L is the length of the bearing and P is the pressure distribution term. And after substituting the value of P, after integration, you are getting this equation. This is the load carrying capacity equation. And this equation is frequently used in solving the problem for plane slider bearing. So you have to remember it properly. And even you should be knowing the pressure distribution equation, which you need to use in future for solving the problem. So this will be the load bearing capacity value, what you will conclude after integration. So you will directly tell after integration, you will be getting this. Okay. So here you know already mu is the viscosity of the lubricant and capital U is the velocity with which it is moving. D is the width of the bearing, L is the length of the bearing, H2 is the converged oil film, N is the attitude value, which if it is given in terms of H1 and H2, you can understand the values of it basically, right? So this is how you will substitute and determine the value when it is given in the internals your examination, right? So you will tell what are these parameters. And one more thing, when you have a load bearing capacity equation, when the load has been subjected to the plane slider bearing, even the shear stress comes into picture. Can anyone let me know why shear stress comes into picture? Any idea? If you know the meaning of shear stress, you can tell me directly. Why do shear stress now come into picture in case of plane slider bearing? Any guesses? Hello, kindly do speak up. It's basic SOM and MOM what you have studied. When you have a top surface and a bottom surface, and when you have a bottom surface constraint and top surface is moving, obviously the shear comes into picture because it is sliding against each other. One is held stationary, another one is moving, another one has a constant velocity. So that this is constant and you'll be having relative motion with in the opposite direction in which it is moving, and hence the shear comes into picture. So due to that, you should also focus on the shear stress which is coming across the moving plane, right? The shear stress usually will be represented by tau, and for that the equation what you have to convert derivation directly, you will throw the equation that shear stress will be equal to h by 2 into dp by dx plus mu into u upon h. So this you should directly throw, telling that this is the shear stress equation which you will be using for the moving plane wherein the shear stress comes into picture. So H will be nothing but the oil film thickness. dP by dx shows you the variation in the pressure, where mu will be the viscosity of the lubricant, capital U will be the constant velocity with which the moving plane is moving, right? So you can tell the parameters what does each claim to be. And later, to determine coefficient of friction, you should be knowing exactly the frictional force. With the help of that, you can try to correlate the coefficient of friction. So for frictional force, and you should think like where for which you are speaking, because the moving plane is at the top of one. So you should speak about the frictional force for the moving plane and not for the stationary one. So be specific when you write. So kindly do write the frictional force on the moving plane will be given as F is equal to L into integral of tau into dx. So with the factor of shear stress, you can correlate the frictional force. Without shear, friction cannot come into picture, right? And this I'm speaking only with respect to the two surfaces wherein one is fixed and other one is moving. So in that aspect, the shear stress has to come forward. Then you can correlate the magnitude of the frictional force, right? So first you will try to correlate an equation for frictional force with the factor of shear stress. So then you will substitute the value of shear stress, then you will integrate it. So the integration here is with respect to 0 to n, okay, the attitude value tau into dx. So when you integrate this, you will come across the frictional force which come across the moving plate. So if they ask you in the examination the frictional force of a plane slider bearing, this is the equation in common what we use. Sometimes they can ask just the frictional force. Sometimes they can ask you the coefficient of friction. So you should be very keen to see which is the part which has been asked in the examination. Kindly select the equation suitably. If they ask you the frictional force and if you show coefficient of friction equation, then you'll be ending with a wrong answer, right? Suppose if they ask you the frictional force also, you should be able to determine the value of shear stress. The value of shear stress is also needed to get the value of frictional force, right? So everything is correlated. So when it comes to plane slider bearing, the components which are usually asked to derive in are the pressure distribution. Once that is done, with the help of pressure distribution, you will be determining the load bearing capacity, right? So once this is done, then you will think about the shear stress, because one plane is fixed, another one is having a relative motion, constant relative motion of velocity u, right? So due to shear stress, then you will correlate the value of shear stress to the frictional force. So once you know the value of 2, you will substitute, you will integrate and get the equation for frictional force. So this frictional force also will be having the components parameters like the lubricant value, right? Then you will be having the velocity value, the width of the bearing, the length of the bearing, the converged oil film H2, right? And the attitude value. So these values will be given as a specifications of the plane slider bearing in the problem. So you have to select the right equation, substitute and determine the value of frictional force. So once the shear stress is known, the frictional force is known, so and even the load bearing capacity value also now we have derived. So lastly, you can in a quick determine the value of coefficient of friction, because you know that mu is equal to force upon load. So sorry, frictional force upon the load. So you know the equation for frictional force already, right? And you know the value for the load bearing capacity. So when you substitute both these values, so F is this one, this equation 4.11 upon 4.8 equation. If you simplify, you will end up with this equation. So you can clearly see the coefficient of friction is varying with respect to the attitude value as well as the converged oil film and the length or width of the bearing. This I stressed you already, right? The pressure distribution during the time of pressure distribution also, it mainly depends upon the converged oil film, because there you will be having the oil distribution. So it will be across the contact area of the top and the bottom surface of the plane sliding bearing. So the friction will be made major at that component, and hence to derive the coefficient of friction, converged oil film H2 plays a vital role. Apart from that, it slides from this end to this end. So wherein this is the width of the bearing, right? So again, that parameter also plays a very vital role. Along with that, the value of n, which is attitude. So these are the three main components which will be varying. So now onwards for plane slider bearing, this is the equation what you have to use. So mu is equal to F by W. You will substitute the value of force, frictional force equation in the numerator, divide by the load bearing capacity term in the denominator. You will simplify, no need to show that simplification and all. You can directly write the coefficient of friction is given by this equation, right? So this is the way how you determine all the parameters. So I hope the pressure distribution equation, the load bearing capacity, the shear stress, the frictional force and the coefficient of friction parameter equations are clear enough. Any doubt associated with this? Hello?
No, ma'am.
Yeah. Please keep the things clear, because this is as easy as you understand. Nothing to mug up. If you understand and write, you can easily claim full marks. Right, so now almost the things are done. Only thing where the load will be maximum, so that you have to understand, right? So the last part here. So after knowing the coefficient of friction, so now if you just consider an pressure distribution curve. So this curve is basically for an idealized plane slider bearing, what now currently we are studying, right? So here the y-axis will show you the value of pressure, and across the x you are plotting the length of the bearing, sorry, the width of the bearing. So when the load is been subjected, across which value exactly the load will be maximum. So you can identify this only by drawing a graph. So when you see the pressure distribution graph over here, so you can claim at what value the load bearing capacity will be higher. Because I told you that if you have a high pressure value, at that point the load bearing capacity will be very high. So it is comparatively good to have a uniform pressure distribution across the entire width of the bearing. but it will not happen in actual when you go with an idealized plane slider bearing. It varies. The pressure varies from one end to the other. But at some particular point, you will be having a saturated value of pressure distribution, which will be termed to be as Pmax. At that position, the load bearing capacity will be comparatively higher, right? So that you have to understand. The same thing has been figured out over here, right? So here the distance x1 will determine the center of pressure. So you have x1 from here till here, and this is from here till here, it is the x2. So what they claim that they are determining the distance exactly x1, at which point the load bearing capacity will be maximum. So to achieve that, what is the equation we need to follow is x1 is equal to 1 by w integral of 0 to b. This is b because we are speaking with respect to the width of the bearing. So integral of 0 to b into x. So this is entire x. What is the distance which has been traversed by the plane slider bearing? From here till here it slides and go back, slides and go back, slides and go back. So this is the actual distance traveled. So that is represented by x. And you know that you have the length of the bearing. That also plays a vital role. So we are taking the length component. And the pressure keeps on varying as it moves the entire width of the bearing. And hence you have to take the parameter of P. So we are considering with respect to dx, and hence we need to write the word dx over here. So this will be the equation what we follow to identify the distance at which the pressure will be comparatively higher, right? So once the distance equation is been figured out where the load will be maximum, you should try to find out an equation for that and calculate the maximum load. So what is the only possibility is here all the values, the L will be given, right? So only the thing which varies here is the pressure. And we have the pressure distribution equation already derived with us. What is that equation basically if you go back? So we have the equation for pressure distribution over here, right? So this is the value of P. So what we do, so we will go to the equation 4.13 and substitute the value of the pressure. So pressure equation is nothing but 4.6. So we'll substitute the value of 4.6 into the equation 4.13. So then you will get simplified and you will get in this form. So x1 by b is equal to something in terms of attitude you will get, right? So after you achieve this equation, this is all after the integration, no steps to be shown. After substitution of the value of p, doing integration, applying the limits from 0 to b, no need to show all those. Directly you can tell after integration and substitution of the value of, after substitution of p and integration, you are getting this equation directly. Please write away and give a name for the equation, right? So now, after that, only the last component which is left out is to know the maximum load value which the ideal plane slider bearing can bear. So for that, you should have a condition like dou W by dou N is equal to 0, wherein this condition will try to identify the maximum load. Okay, so the film thickness, what we are selecting, mainly leads to the maximum load, because you know that we have done many trials and errors and characteristic features analysis and all, how to determine the required film thickness to get the maximum load bearing capacity. Usually the film thickness plays a vital role, because depending upon the film thickness, the pressure distribution also will be varying, and based on the pressure distribution, you can see that where the maximum load you will come across. And hence this is a condition what you have to understand. Here all the parameters are with respect to the attitude value. So we are integrating which is needed the value of W with respect to N. So it is dou W by dou N is the condition what we follow. So when you claim dou W by dou N is equal to 0, right? So the above equation will be figured out in this way, because in this equation we will be taking the attitude, the eccentricity ratio as 2.8, right? To calculate why it is n 2.8 also, there is a huge lot of theoretical approaches, right? So don't go into so much depth. Many researchers have done all those mathematical calculations. They have claimed that the value of n will be 2.18 for an idealized plane slider bearing to get the maximum load condition at a particular distance. Okay, so directly we are using the value of n is equal to 2.8 into the equation 4.8. Yes, so using equation 4.8 in the above equation you will put 2.18. For 4.8 equation, this is a load bearing capacity. Without using load bearing capacity equation, you cannot find out what is W max. So to know W max, you should be knowing some numerical value for the attitude, right? So this value you cannot claim theoretically because we haven't done any mathematical modeling and theoretical approach of analysis. But the other people have already done and proved n value as 2.18. So you are substituting the value of n is equal to 2.18 over here, and we will claim an equation for maximum load. So when you substitute those values, so this is the equation what we get. So W max will be equal to 0.1602 mu UL B square upon H2 square. So this is a constant value. So mu we will be knowing it as an lubricant, right? Viscosity of the lubricant. U will be the velocity with which the moving upper surface is moving. L will be the length of the bearing, capital B will be the width of the bearing, and H2 will be the converged oil film. So all this data will be given in the numerical problem. So you will just substitute and find out the W max. See this, you will usually get a problem on this wherein you need to determine many components right from pressure distribution. Then you will calculate the load bearing capacity. Sometimes they can ask you just load bearing capacity. Then you have to use this equation. If they have asked you to find out what is the maximum load bearing capacity, you should also be knowing this equation to find out what is the maximum load bearing capacity of a given plane slider bearing. Apart from that, they can ask you the shear stress value, pressure distribution. So you should be able to use this equation and find out pressure distribution. Then later, they can ask you to determine the shear stress. You should be specifically knowing the equation for shear stress, and you should be knowing a equation for frictional force because they can ask even frictional force. So after all this, you have one more component which could be asked. That is nothing but the coefficient of friction. So if they ask you coefficient of friction, you should be able to find out this. And also, sometimes a theoretical short note could be asked to derive an equation for so many things and claim how a load could be maximum at one particular point. So then you should be able to figure out this graph and explain how the load will be maximum at which point, and finally use the condition dou W by dou N. Just write an equation for load bearing capacity, put the value of n is equal to 2.8 in that equation, substitute and show that this is the maximum load bearing capacity equation, how we can claim for solving the problems. So this is the way how you have to able to smartly put forward in the examination. Nowhere they ask you the integration steps, simplification steps to show. You should be able to tell what are the equations you are using, what are the parameters, what are the ranges you need to use for integration, why you are using that, what is the boundary condition, how you calculate the constant value, how you substitute and get the equation for pressure distribution. So which is the equation for load carrying capacity, which you have to substitute in the load bearing capacity equation, and after simplification what you get, right? In this way, if you try to figure out the actual flow and show all the equations related to plane slider bearing, you can easily get out of out marks. So this is the thing what you have to understand. And in the next class, there is little bit more theoretical things what I have to explain you. So once that is done, we will be going for solving the problems. So any doubts in the derivation of load bearing capacity, pressure distribution, shear stress, frictional force, coefficient of friction, and maximum load bearing capacity?
No, ma'am.
Is it clear enough?
No, ma'am.
Okay. So
Yes, ma'am.
yeah. So please ping me up at any time if you have any doubts. So if you understand the concepts, it is a really mark scoring subject. You can solve any problems given if you are thorough with the equations and get a good marks. So ultimately that is the goal what you have to achieve. So please work accordingly. And now I hope everyone have written your name and USN number in the chat room. And one more thing, your third internals has been postponed because the term has been extended from December to January, right? So in that aspect, it is 4th, 5th, 6th, I guess, and 7th of next month in January. I think Kanishka had asked me to clarify. Is he there? Mr. Kanishka, are you there? Okay, just inform, and this is the information not only for Kanishka, for everyone. So it's good you have time. We can cover the things still better, revise some question papers, and make yourself ready. Any doubts, you can call at any time for any clarifications. Please don't hesitate. So let me call the attendance. I don't have attendance register with me as I am at home today. So I will just note down the students' name who are there in the list, so the others will be marked absent. So time being, you people write your USN in the chat, USN and the name in the chat room. Alok?
Yes, ma'am.
Alok,
Yes, ma'am.
you just tell me your USN number, Alok. Ending number.
Not 4.
Okay, thank you. Anil Kumar? Anil Kumar? His name is there, he's not answering. Beldar Mohammed?
Ma'am, 012.
012. Okay. Next, Chaitanya?
013, ma'am.
013, Chaitanya. Okay. Chetan Kumar? I think he has dropped a message.
Ma'am, present, ma'am.
Yeah, 015, is it?
Yes, ma'am.
Okay. Danush?
Present, ma'am, 025.
025. Dheeraj?
017.
017. Gunasagar?
Ma'am, 402.
402. Himanka?
Ma'am,
Himanka?
20, ma'am.
21.
20,
Oh,
ma'am.
yeah.
I'm 20, not 21.
Okay, 20. Thank you. Kolepara Srinaga?
Ma'am, Abdul 001.
Yeah, Abdul, just a second. Kolepara Srinaga, tell you yourself.
023, ma'am.
023. Fine. Abdul, where were you when? Okay, I didn't call your name. 001, is it?
1BY17ME001, ma'am.
Yes. Anil
Ma'am,
Kumar.
ma'am, you called the other Dhanush. Have you called my name out yet? Because are you calling it out in the list of how the Google Meet is showing, ma'am?
Yeah.
Okay, ma'am.
What's your
Ma'am,
USN?
Anil Kumar.
Ma'am, my
006, ma'am.
USN is 1664.
What's your name? It's showing as Anil
Dhanush.
Kumar.
Yes, ma'am. 006, Anil Kumar.
Dhanush, it is
Yes, ma'am. 1664.
1664. Okay, thank you.
Okay, thank you, ma'am.
Thank you, ma'am.
Yeah. Kolepara. Okay, where I ended.
001, Abdul, ma'am.
Yeah. No, as per the order I was going, you people interrupted me. Okay, Himanka is done. Kunal Raj?
24.
Everyone type your name and USN. Dhanush? M. Dhanush?
025, ma'am.
025. Okay, Meghanatha?
Present, ma'am.
Your SN number. Meghanatha, your SN number. Okay, Mohammed Junaid.
029, ma'am.
029. Okay, Shri Prasad.
Ma'am, 030.
030. Okay, Niharika.
031, ma'am.
Okay, 031. Nihar. Nihar. Nikhil.
033.
033. Okay. Neerab.
Yes, ma'am. 035.
035. And Rishabh.
041, ma'am.
041. Roshan.
Ma'am, 043.
043. Sagar. Sagar Datmatur.
045.
045. Sanjay Raghav.
047.
Okay. Shiva Krishna.
18 ME 406, ma'am.
406. Okay. Shobit.
Ma'am, 050.
050. Siddharth B.
051, ma'am.
051. Subramanya.
Present, ma'am.
USN number, please.
57.
Tirumana Sethi Rohan. Rohan. Tirumana Sethi Rohan.
32 present, ma'am.
Okay. Ullas. Ullas. 60. Done, Ullas. Varun.
63, ma'am.
63. Yogananda.
410, ma'am.
Okay. I think that's all. Fine. Everyone. Yeah. Yeah, Ishan.
018.
Where were you, Ishan?
You didn't call.
I'm sorry. What's your USN?
Ma'am, 018.
018. Any students whom I have missed to call the attendance?
32 present, ma'am.
Nihar,
Ma'am,
is it?
1664. Have you marked it, ma'am?
Nihar, just tell me your USN. 16?
32.
6.
16 ME 32, is it?
No, ma'am. His is 17
17.
ME 32 and
32.
mine is 16 ME 64.
Danush is 16 ME 64. Yeah, I have noted down yours.
Okay, ma'am. Ma'am, and Nihar's is 17 ME 32.
Yeah, I have corrected it.
Okay. Thank you, ma'am.
Yeah, fine. Then take care. Have a happy weekend. Be safe. And let me meet again.
Mark, ma'am.
Abdul, I have marked. Abdul, USN is 001, right?
Okay, ma'am. Thank you. Yes, ma'am.
Yeah. I have marked it. Fine then. Take care. Have a good day. See you back in the next week. Bye-bye.